Seismic activity near Santorini, canyons in the Colorado Plateau, crumbling foundations, and downstream channel response to the Eagle Creek fire. Welcome to Geology Hour. I'm Alyssa Smith.
I'm Carrie Gordon.
And I'm Cody WIlbur.
So this is a bit where I'm just going to summarize some recent things that have happened in the geology world. So starting us off with a picture of the wooden shoe tulip field, which is very seasonal right now. So today, the stuff I'm going to cover are going to be recent earthquakes near Santorini, how to carve canyons in the Colorado Plateau, and then problems that can occur with pyrrhotite in concrete. So I'm getting us started over here in Europe, just turning back the clock a little bit to January of this year through just recently. We're going to zoom in here to near Santorini in the Aegean Sea. So recently there have been a number of earthquakes out here, thousands of them with epicenters between Santorini and Amorogos, which is up to the northeast of there. And it's been kind of the strongest one there at about a magnitude 5.2 and others up to about a 4.0. So recently the quakes have been slowing down, so it hasn't been as much activity by people in the area. So this is a map that shows a cluster of the earthquakes between January 29th and the 6th of February. And that was, I believe, when the activity was the greatest. And this is from the Helmholtz Center for the Geosciences. And most of these earthquakes are pretty shallow, so between 3 and 15 kilometers depth there. And this is a pretty small map, even though this was the biggest one I could find. But the size of the dots on this image show the relative size of the earthquakes. So mostly the colors are visible here. So you can see varying sorts of depths, but all pretty shallow. Earthquake swarms in this area are actually not uncommon. It's something that they would expect in this area. Santorini itself is between two different volcanoes. And the current sort of activity that's been going on, they can't rule out that there's going to be more future quakes or even that there's an eruption, but these events have happened before and they haven't led to eruptions. So that's kind of where we're sitting at now. So originally there was a state of emergency that was put out for Santorini and the nearby islands, but that started with a bunch of school closures and rescuers dispatched and whatnot. But as of mid-March, Santorini has been declared safe to visit. So they've put in a bunch of new seismic monitoring, not expected, but then again, they can't rule anything out. So that's kind of what's been happening on Santorini. Now we're gonna head west or east really far to the central Colorado Plateau. So there's a summary article recently published in EOS and another longer paper in AGU Advances. So I'm going to start us off looking at the Colorado Plateau, which if you're not familiar with it, it's in the Four Corners area. So Utah, Colorado, Arizona, New Mexico. That's what this little outline is. And the Colorado Plateau is pretty, it's a big question for a lot of geologists in a lot of different ways. There's been about 2 kilometers of uplift in the Cenozoic alone. And this is an area that's mostly high deserts, but a lot of forests. And the rivers that are there drain via either the Colorado River or, which is, I think, something like 90% of it. And the rest of it goes through the Rio Grande and the tributaries of either of those rivers. So this study was looking at erosion in the Colorado River's history. And the biggest question is that there's been this variable incision throughout the Pleistocene, and they don't really know why. So that's what these authors were aiming to try and figure out. So this is a map of the study area, and it's just a number of canyons throughout the central Colorado Plateau. And this is really small, so let's zoom in a little bit. Wow, it's like magic. So they were predominantly looking at these canyons that are numbered here. I'm going to call us into Meander Canyon to show the sorts of work they were doing. So what they were doing is using a few different methods and looking at terraces. So these are, this is an example of one of the terrace profiles that they were looking at. And this one's from Meander Canyon. So what they were looking at is luminescence dating. And with that, they can estimate the time that it's been since mineral grains were exposed to either sunlight or extreme heat. And then the other method is isochron burial dating. So with that, they use terrestrial cosmogenic nuclides, which is a really fun phrase you don't get to say a lot, specifically beryllium-10 and aluminum-26, to determine how long material there has been at the surface. So with the luminescence dating, they used buried samples. So these are expected to have been shielded from solar radiation, and they took these from just sand lenses in the terraces. And then with the isochron burial dating, they used clasts of whatever lithology was present to measure for those different cosmogenic nuclides. And then what they did with both of these different methods is they got independent ages. So kind of like a check to see, make sure that these things are lining up so they're reliable. And with that, they were able to reconstruct the incision rate history. So you have to assume that each of these terraces represents a different level at which the river was at and cutting through. So you can see that the ages get progressively younger heading towards the bottom, as that's the way it was incising. So it looked like it turned out pretty well for them. So what they found from this is that there were two periods of incision, the first being a really slow period in the early to middle Pleistocene. And what they attribute this to is a relatively stable landscape. But then in the middle to late Pleistocene, there was a bit of a shift. And actually what this was is it was lag from an earlier change, which is where the propagation of the incision at the Grand Canyon to kind of propagate it up the Colorado River. And so the base level, which is the deepest point to which the river can erode, began to fall. And so that was a pretty rapid time. And the thing is, and there's so many mysteries surrounding the Colorado Plateau. I took an entire class on this in my master's. But what they found is that the rapid period only accounts for about 25% of what they would expect to be the exhumation over the late Cenozoic. So it was a really important study, but it just kind of highlights the complexity of this area. Now we're going to move on to problems with pyrrhotite in concrete. So this is an article that was published in EOS in January of this year, and essentially looking at home foundations that are crumbling, and they're blaming it on one little mineral. So essentially what's been happening is in New England, there have been a number of houses where their foundations have started to crumble. And they've started to attribute this to pyrrhotite in concrete. And there have been similar issues documented like this in Canada and potentially in Ireland as well. It's been really difficult to pin down, but you can see some of the damage there that's been caused by this process. So pyrrhotite is an iron sulfide. This is a little image I took here from MinDat for all the mineralogy fans out there. So this is the mineral formula. It's an iron and sulfide compound. So you'll have essentially, there's a lot of things that can be considered in pyrrhotite group. Minerals are a lot more complicated than we like to imagine, but there's one less iron in each of these minerals than there are sulfurs. So that's the general formula there. So some of the general properties, this is a metallic mineral, a hardness of 3.5 to 4. So you can kind of compare that. It's going to be a little bit harder than your fingernail, which is a 2.5, but softer than glass, which is a 5.5. And it's a bronze mineral, and it's either monoclinic or hexagonal shape. So the one I have here is hexagonal, but was not a lot of monoclinic representation in the models I could find. So the occurrences, so where do we find these minerals? Mostly going to be some in mafic igneous rocks, like basic, but that's mafic. And then also it will occur in veins, which I think is the most common thing, and in metamorphic rocks. So what's the problem? So pyrrhotite oxidizes really easily, and that can be a big problem if you've got a lot of water in your rocks. So this is a chemical reaction for the process, and I highlighted the two things we want to look at. So you have the pyrrhotite, that iron sulfide, combining with oxygen and water, and then it will produce some amount of iron, some hydrogen, and then sulfate. And this is the problem. So if the reaction stopped right here, things would probably be okay. But the problem is for foundations that the secondary reaction will happen, and you'll have this sulfate combine with whatever else in the material and create sulfate minerals. And the issue there is that these minerals tend to take up more space, and this is what can lead to cracking in foundations. So this here is a map put out by the USGS in 2020, and this shows areas in the United States where there could be pyrrhotite. So the red kind of coral color is what they called pyrrhotite permissive geology. And so those are rocks that very well could contain pyrrhotite. And those dots are areas in like Mindat, and there's one other source where there's been kind of confirmed deposits. And so this is important to consider because if there are places that are going to be sourcing local rocks for concrete, they need to consider whether or not these have pyrrhotite, which is going to lead to cracking. So just something to think about. So this study, again, is from Connecticut and Massachusetts. So somehow it hasn't spread, but there's some complications there too. So namely, damage from this process can take 20 to 30 years to become visible. So it's not a very fast process. And the other problem is that there's very limited testing available for this problem and even less regulation. And so this leads for a lot of room for there to be research on this. And there's a conference that took place, and now my notes are behind, so I can't. Okay. And so there was recently a conference on iron sulfides in building materials, which is like super niche, and I think that's super cool. But it's definitely something where there's a lot of room to grow. So what's been happening kind of on the ground is a lot of sort of advocacy groups. People are pushing for legislation and financial relief. This is a horrendously expensive problem. If I could see on my notes, I believe it's, in the like several $100,000 to replace some of these. The picture kind of shows you have to lift your house and remove the foundation, and so it's huge. So what some of the people in the article had said is it was almost like getting a cancer diagnosis for your house. It was like such a serious problem that basically people are buying these houses and then everything falls apart, no pun intended. So kind of the next steps forwards are going to be increasing the amount of research to figure out how widespread of a problem this is, and also then to put regulations in place to protect people where this may happen in the future. So I must have talked really fast. So that's my bit for March. And here's a view from the Metolius River outside of Sisters. But yeah, check in next month and we'll have more things to talk about.
Yeah, yes, Alyssa, you did just breeze right through there. However, Blue's got a question. Has there
Excellent.
been any research into how local climates can affect the speed of the reactions?
I don't know that they had that in this study. And there's so much that needs to be done from what I'm seeing here. And the fact that, they're only seeing this in Massachusetts and Connecticut, is that's where they're recognizing it. And so I think that a lot of it is like, I don't know if this is happening other places and people aren't realizing that's what the problem is. But I'm not quite sure if there's a connection between the local climate. I would imagine there is because it's something that's moisture driven. And it's also a really muggy part of the country too. So definitely possible.
True. So the other thing that I was keying in on, besides within the United States and the geology you were looking at, is the fact that the Atlantic Ocean, you know, Ireland used to be smacked up against Massachusetts
Yeah.
and New England. So similar rock types and similar climate. So I would kind of guess there's going to be something along those lines. Wes had a comment that is that no regulations regarding this problem will be happening soon, based on just some of the things going on. But here's my take, having worked in the mineral material arena my whole career for the Forest Service, is that there are a lot of testing regulations that are out there. And I know that some of these things are, it's kind of cool that they're figuring this out, but there are tests out there for looking at those concrete and the rocks that are being put into the concrete type of regulations. So there's work that goes on with that. So
Yeah,
I got to back up to the Grand Canyon be-
sure.
because I lived in Flagstaff, and that was one of those amazing cuts in the earth where I look out here at the Crooked River, and it's 16 million years to excavate the canyon I've got south of town here. And we're looking at, what did I just write down? 300, 350,000 years is that what that's that was the slow, no, that was the faster erosion period, right? But it
Yes.
only accounts for 25%.
Yeah, and I think that this, like I was kind of hinting at, so actually, when I was living in Flagstaff doing my master's, I took an entire class on Colorado Plateau uplift. And so the exhumation is just the other side of the coin there, because what goes up has to come down, right? That's erosion 101. And I think that basically it seems that there are a lot of researchers trying to attack this problem from a lot of different angles. And so I think that with these terraces they're looking at, it's just a period of it. And I thought what was really interesting about this is that there was a lag due to, I kind of started hinting at it, essentially upstream from the Grand Canyon. There was a lag in that the absolute gutting of the earth at that place. It took several million years for that to reach upstream.
Mhm.
So as far as like the other parts that are missing, I don't know if it's just, attacking from the wrong angle or what it is. It's really complex and nobody seems to have anything that adds up correctly, which is wild.
So part of what, and this is just me for the 5.5 years that I lived there, but my observation was if you have changing sea levels, then you're going to have that lag time before it finally gets up there. But I'm thinking from Cody's talk, we're probably going to see that mini landscape going on with changes that happen because we've got the big with the Grand Canyon, but what we see on a smaller scale are those erosional reactions that happen with some of our fire landscape and things like that. Blue was talking about the potential for moisture introduction was what she was thinking of, that they were thinking about, and that regular freeze thaw cycles as well. And given New England, and that is the place, engineering, that is the place that they came up with the idea that, oh, deep freezing cracks asphalt. Maybe we need to redesign the roads to handle that so that they last longer. So actually, Blue, you may be onto something there. And then Clark points out that another factor to consider is the aggregate itself, because goes into that concrete can make a big difference.
Yeah, and I think that was what they were kind of trying to get at with this is that the stuff that's being used in the concrete itself, the aggregate, is what is, causing this. So um yeah, it's a big problem for a lot of people, and I expect we're going to hear more about that.
I think
And
Blue may be launching into, hey, this might be a good PhD research.
yep, write it down. There's no shortage of questions in geology. We could have probably just about everybody on the planet become a geologist, and we would still run out of questions to ask. Or we still wouldn't run out of questions, rather. We'd still have a ton of things that we're looking for answers.
And so here's a positive side. I talked to a group of fourth graders last week. Um, 80 of the little guys. I didn't know their little butts don't take up very much space when you're talking to them when they're seated on the floor in the classroom. So a lot of their questions were very insightful, and they were asking about how is volcanic ash made? And so I'm hoping that we have a new crop of young, interested geoscientists coming along.
That would be great because like I said, there's a lot of things that we have left to do.
Anybody else have any other questions?
Yeah, this is Carol. I have a quick question. Thinking about the distribution map of that you showed of where the problem is occurring in the United States, it's kind of well, I'm just wondering about the distribution and is it because the materials they're using for the concrete are coming from local sources?
Yeah, I think that's the general idea. I was trying to pull up the map and then I lost my Zoom, so I don't know where everybody went. But yeah, I think that's why they're trying to see if there's that connection. Because yeah, there's no reason to move things that far if you've got local stuff available.
Yeah, I guess I wondered like are they aware that the pyrrhotite is in there? You know, is it
No,
being used intentionally or as or unintentionally, I guess.
It's definitely not intentionally. Is everything I gathered from my reading. Um, but it's the fact that it could be present that people haven't necessarily been testing for in the
Oh, I see.
past.
Okay. Yeah.
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 And since it takes a while, it takes, 20 to 30 years for it to become a problem. It's something that it's like, I don't even know, that might just get worse as time goes on.
Yeah.
Who
Wow.
knows?
and now here's Cody Wilbur.
Hello, thank you. Thank you everybody for being here. My name is Cody WIlbur, and I'm a second-year graduate student at PSU, working with Adam Booth, and my project is the downstream impacts and channel response to post-fire hillslope processes as a case for Eagle Creek on the Columbia River Gorge. I did not take this picture. It was taken by this guy, David H., and it's from Vista House. You can see Rooster Rock, and Eagle Creek is right around the corner from this bend here. So just to start out, just a background, I'm sure a few of you probably know this a little bit, from experience more than I do. But on September 2nd, 2017, the use of fireworks illegally within the Eagle Creek watershed set off a destructive wildfire that burned about 200 square kilometers. This is a before and after image of Google Earth from the year 2017, right before the fire, and then the next year, sorry, um, the next year out of the fire, just to see like the scale at which this watershed was burned. I'm sure all of us also could see that when you drive down I-84, you can start seeing burned trees, and you can start to see that by like mile marker like 36, I want to say. The Forest Service's emergency burn response group was the first to characterize the soil burn severity of that watershed, and you could see Eagle Creek and Tender Creek were both susceptible to burning. For the sake of this project, there's not really any distinction between the soil burn severity between Eagle Creek and Tanner Creek, since both areas kind of were subjected to the same kind of fire in the same fire that started it too. I'm going to talk about some introduction to this project. So hillslope processes are the major geomorphic agents in mountainous forested terrain. They're able to transport sediment. They're highly influenced by our climate, and it can be hazardous to people and infrastructure under the certain conditions. Sorry. We'll go to the next one. So yeah, it's shown from prior research so far that wildfires can alter the geomorphic response of hill slopes that transport this material downstream, and that's usually driven by large seasonal precipitation events here in the Pacific Northwest. It's just unlikely that the drivers for this are specifically fire or they lead to one or the other. So with this project, I'm trying to look at what's happening for a particular part of the river channel following wildfire. A study by Jackson and Roaring found a pretty key part into this, that wildfire introduces a decline in root strength, a hydrophobic soil that leads to increased erosion and altered infiltration rates. This is a main driver for what's moving surface processes after wildfire. As you can see from the diagram here, it seems that the soil becomes burned in this water repellent soil layer that we have here in the Pacific Northwest that's usually more, holds a lot of moisture, is now decreases in depth after the fire. This leads to a water repellent soil layer that's actually not at the surface of the soil, but is lower now. So you can have this loose, unconsolidated material that now is sitting right above a more water repellent soil layer. And this is another diagram to just articulate and show what happens to the hill slope after this hydrophobic soil layer is created. Again, the transpiration decreases. You get all the root cohesion is now like burned and lost. So a lot of material is able to be like washed downstream with high precipitation events, or even slow like atmospheric river events even. And it can lead to debris flows, shallow landslides, and other hazards throughout a landscape that's been burned by fire. I won't read all these quotes, but these are all different papers that in the past 2 decades now have like hinted at different parts that are affecting Eagle Creek in this area because of its susceptibility of shallow landsliding, and now that it's been burned by the fire. So it seems that they're fairly unanimous that the geomorphic response is a lot of shallow landsliding that maybe occur in an area susceptible to burning. And this image here on the right is actually a large shallow landslide that occurred Eagle Creek in 2021. And you can still see much of it, and it's all the way up the slopes here. But it's not very deep in depth at all. It's not like a deep sea landslide. It didn't cause catastrophic failure. It just, gave way, I want to say maybe about a couple of feet of soil all the way down into the channel itself. And something that's been really important about this was that noticing that this susceptibility to shallow landsliding may last up to 10 years following a wildfire. 2017 was about 8 years ago, so this is kind of in the time where looking at what recovery looks like, does it take 10 years or is it actually longer? But we'll see that as we go. More hints to what's happening in the early years following the fire are from other researchers that have done different work on post-fire. Like in this one here is to the right was for reservoir, and notice that there's a huge amount of like loose and ash and like fine sediment that's deposited in the first 1 to 2 years following a wildfire. That's not related to coarse sediment that's depositing that year. But however, actually, after all of that is washed away, it seems like coarse sediment actually begins moving again. Again, in this diagram here might show that, vegetation regrowth, coarse material increases as the fine material is washed downstream. So it seems like there's this delayed response in coarse sediment deposition following a wildfire. And that may last up to several years. Again, Eagle Creek fire was 2017. That's about 8 years now. So the purpose of the study is to characterize these changes that's been occurring in a watershed that's been burned and using Eagle Creek as a proxy for that. It's expected that landscapes are, will return to pre-fire conditions, but over different timescales and different variables are affecting those. Hillslope's recovery might recover sooner than the channel itself. And so this gap in understanding between these interactions between both the Hillslope and the channel itself has led to this project that I'm kind of personally, interested in, just because this is a new interesting side of geomorphology, post-fire geology, and it's just kind of happening in your own backyard. And I just think that's a good thing to focus on. And this image here is one of the gravel bars that makes up the lower reach of Eagle Creek. And if any of you have gone to Eagle Creek for a trail or just for recreation, you probably know where this is, but there's also tons of shallow landsliding that occurs all throughout the Hillslope and the channel. And every season after the rain, you can start seeing more and more. I just saw more the other day. So just to talk real quickly about what channel processes are, if we're focusing on bed load within this channel, is that it takes a particular amount of like force and flow in order to move this bed load material. This diagram shows that the normal bed load that makes up most of the Pacific Northwest, armors all of our river channels. It moves relatively slow throughout the year under just normal conditions. Usually it has to be in a much larger flow event or a flooding event that's really going to like alter and move the bed load material that's sitting farther below the bed itself. And I've highlighted this little region here because this is kind of like the particular conditions that I'm looking for in order to track how these bed load particles are moving. Most of our material here fits in this 10 to 100 millimeter range for cobbles and not necessarily boulders, because those move on at their own time scale. But it really requires a certain like I almost say like a Goldilocks zone of what's required to move this material downstream, and that's usually in the form of high flow events or flooding events that occur again seasonally here. In order to track this sediment motion, I'm identifying the changes in the elevation of not all, but the lower reach of Eagle Creek, where we're characterizing it as like a post wildfire sediment, and that's kind of made up as all the bars that make up the lower end of Eagle Creek right as you enter. If you're familiar with Eagle Creek, you kind of can tell where this lower end is before you actually reach trailhead. And this here is 2 images from the terrestrial LiDAR scanner itself that I'll talk about more about later. But you can see here, this is almost this, wow, yeah. almost this time last year where flow was relatively low. This is kind of coming out of the rainy season, whereas this is, earlier, I want to say earlier this year, a few months ago, and there's actually much higher flow. And this is kind of the onset of this early weather pattern that we have here, where we start getting more rain in the fall, and then drastically it comes down into our river channels itself. And I'll come back to these images later on and talk more about the scanner and the process later, but this just articulates and shows that there's a distinct difference in the elevation of these beds exposed from water, and that will show up on the LiDAR scanner. And so doing this, I'm trying to look to answer these questions is what storm size is required to promote this this movement of material, sorry. And what is the bedload transport rate now, and is at a steady state since the fire? Both these are kind of to gauge what recovery of a fluvial system looks like following a wildfire. This study here was actually a study by another PSM graduate student here at Portland State University that was looking at water temperature, turbidity at Eagle Creek and Tanner Creek following the fire, and this is in 2019. So this is something that I'm going to use later in my analysis to understand what steady state was. This is kind of like an early distinction of what was happening after the fire. But I will just notice that, or just want you all to notice that there are peaks in this, more wet season that we're in now this year, but in scale, not as large. But there is 1 or 2, maybe even 3 peak flow events that realistically should be moving bedload material. That's all in relation to precipitation changes too. So the methods I'm using to do this, again, I'm using repeat terrestrial LiDAR scanners before and after flow events. I'm using the old tried and true Holman pebble counts because somehow that's the best way to get grain sizes, even if it's 300 rocks 4 times a day. It's tried and true. It seems to be work the best, and so far it's already come off as consistent results opposed to other methods used early on. I'm also using water stage and infiltration measurements to catch these high flow events. And then, as I mentioned, I'm going to model the before and after with some of the variables and numbers that I calculate from the analysis to see what it is like at steady state and what it is now. And I'm going to show this again, but this is actually my own water stage data that I started gathering once I set up a gauge system at Eagle Creek off the original USGS grade system that was shown before. So first things first, I had to establish terrestrial LiDAR scan sites. So these sites need to be able to both have fixed objects in the back so that I can align them consistently throughout. They need to be able to have a lot of the gravel exposed, and in the way that I set up these sites, they're all in view of another. So when doing the analysis, these will all be able to be clipped together into what is a time series of Eagle Creek's lower reach at a particular time in the year. And then over these peak flow events, I'll be able to overlay them to each other and track the motions between these storm events and between these LiDAR scans to characterize how much bedload material is moving, how much surface elevation is changing over the course of different seasonal events and flow events. So this is the lower end delta that I showed earlier as a LiDAR scanner, just to show that kind of the base of where I do a lot of this, and I kind of work my way up. So this is a little bit upstream, there's some more under the bridge, and then but this is looking downstream, and then this is looking upstream of that site. And I'll just note for fun, feel free to keep these pictures of these like little stable features that are here now for later discussion. So this is a map that I made to kind of just show where these scanners are placed and where these sites are placed. So again, the scanner can scan at about 360 degrees. The range is pretty wide, and I can have stable features like these bridges and these pilings that are used to align these later on in the analysis. But each scan will build off of the other as it works its way up, all the way up to this upper reach where I started earlier. And this is the same hatchery. Trailhead is this way, and there's actually some concrete structures that the Forest Service had installed to monitor the flow. That's right here in the farther upstream. So that's why the lower end is what we're using to track this bedload material, since there seems to be enough of these gravel bars that make up to actually be able to track this over time. So again, yeah, Holman pebble count method, if no one's familiar with it, and I'll just go really quickly. It's the tried and true method of walking a cross section and picking up rocks and measuring their intermediate axis for about 300 times. You put that into some Excel sheets and you can kind of get a median grain size, a mean grain size, and you can tell the difference between these. And so this is actually this is the graph of the first pebble count that I've done before any flooding events. This is when I first established all these sites. I did it on each one of them, and you can kind of see that the delta and the upper, you can see the difference in these and how the upper reach should have the largest grains while the lower reach has the lowest grains because the smaller material is able to move at a much faster rate in comparison to larger material. I haven't created another graph since the initial, but from firsthand accounts of doing new measurements in the last couple months, I've already started to notice this downstream finding is occurring in real time, and as well as hydraulic sorting is happening in real time. And some interesting analysis I did here is that the intermediate in the bridge from a t-test of a mean grain size, they do not differ very much. So it's actually going to allow some ease when it comes to doing this, that the difference between both the bridge and the intermediate site, since they're so close together, that might be able to be called its own, bar, its own unit of bed load itself. So getting water stage, that is the trick. So these are some images of how I did this. So I purchased some telemetry, sorry, it's hard to say that word, telemetry sensors from HydroView that is input into this steel pipe. So these sensors are coming out here and they're installed right at what is like a normal flow level water stage for Eagle Creek. And this was set up during I want to say summer of 2024. Yep. Yeah, it involved digging out the bed material itself right between these larger objects that would almost anchor this 70-pound concrete sensor bucket in the channel itself. And it was all fastened with bedload material that was used. And this is coming off of right here. This is coming off of the original gauge that was installed by Kelly Gleason and her student before. However, both Nadi Bergman, who's been helping me with this project, and I thought that putting the sensor out in the channel would get a better accurate representation of what water stage is during even a low event. So even here, this is considered what is, maybe a 0 foot water stage for the sensor, but is actually 2 feet in depth. And we maybe think that might have been an issue with Silas's earlier report where his water stage wasn't as high because it was only situated right here on the bank itself, not actually in the channel. And so for determining water stage and threshold for motion, that's kind of going hand in hand with these LiDAR scans before and after peak flow events. So I put these little lines here to bracket when scans are done. And these are lines here perpendicular to that to show what that threshold for motion could be, or we could see after that time. So we had a peak flow event here in early November. I went to scan mid-November when the flow was lower so that I could see how much that material moved. And I didn't include one, but there is an initial scan here. So each of these blocks will represent different thresholds for sediment motion, for coarse sediment motion. So I will turn your attention to this one here, though, because this is where things started getting a lot more interesting for what I expected for this project and what I'll talk more about as the talk goes, because right now we're here at what has been done and what I'm doing. But because of some things that have happened, there's some things that need to be changed. So December 26th, about 8 a.m., this is all recording in live 6-hour time. I'm receiving all this all the time. It just disappeared. This should be recording. I should have data today. However, we do not have data today. But I can look back and I can see that this steepness in water stage over time is extremely fast and extremely steep. It actually goes to here and it goes about 5.5 feet. Just for the sake of this, didn't show that, but it went from 2.5 feet to 5.5 feet in about 6 hours. So there is no gauge anymore, actually. This steel pipe that was reinforced with cement and steel was actually severed in half. The sensor here separated here, the pipe separated here. And this is why the sensor was off. At first, it's thought maybe a tree fell on this old station here. But just from first appearing on the scene after this, I was out of town at the time, so I wasn't able to get out there the day after, you can see water levels that are almost about here, from like down limbs, down debris, bed material that's kind of plucked in really odd places that they shouldn't have been, just to consistently show that this flood did actually reach to levels at 5.5 feet that I could observe from my own data. However, the inconsistency afterwards is there. So I said one large event. Actually, there's been 2 large events. In the first event, yeah, the system that I set up in summer completely destroyed. So I've already been looking at other ways to track this water stage level. And because I didn't have that information, this picture here is actually from the news. This is the image of Eagle Creek's entrance to the trailhead. This is a wall here, and this is about 7 feet above the wall here, the retaining wall that the parking lot is, and everything like that. And this image here is actually from someone at the Cascade Fish Hatchery. This is right above, right below the gauge itself that I set up, and using these pilings as ways to kind of track when this water stage reached the height that it did. This is about 5.5 feet to the bottom, and this is about right at peak flow from what one of the salmon hatchery guys told me about. So there's been a big update for the since December. So in the last 3 months, I've kind of been working a little bit more about how to catch these floods events, and nor did I expect there to be another one that was actually at a larger magnitude than the previous one in December. And this is seen on other surrounding gauge stations in the system, because again, mine went out, but you can still see here, this isn't a great indicator, but it is a good signal. This is the Columbia River Dam, right below Eagle Creek, right below Bonneville Dam. And it also showed the signal of extreme steepness in water stage change right at that time in a very short amount of time. And this is the Bull Run right above Lower Flume, and this is actually indicated this is most likely due to a malfunction with the software at the time. But each gauge system operated by USGS in any close proximity to this region showed a similar signal to what was occurring on December 26th. But I want to take us real quick to what happened a few weeks ago, because we saw it again, but we saw it at a lot higher scale. And unfortunately, I didn't have gauge data or real-time water stage to show this was happening. I had to use firsthand accounts. I had to check my phone. I had to see the news, see the weather. I was watching atmospheric river events. And this prolonged atmospheric river event led to, in what could have also been like a rain on snow event, leading to more water in the system. Again, more debris, like more water, higher water stage, another peak flow event that, at least from what record could show and from firsthand accounts, is a much larger magnitude flood than has been seen in Eagle Creek, at least in the last 4 years. And this is again from salmon hatchery folks who were telling me this. So this is different times since those floods. So this is back in January. This is when terrestrial ice scanning was done after the flood, the initial flood in December. This is that, retaining wall that I was mentioned. This is again after the flood levels went down, but there's numerous accounts of debris all lined up on the wall. There's dirt. You could see that the water was there. And then this is again the site, right at the site. You can see water levels up here, but this is bedload material. All this is bedload material. And there really shouldn't be any reason why bedload material is about 100 feet up the bank, maybe 2 feet up in elevation. So this site's already honestly gone through a lot of changes just in the last year that I've been monitoring it. And the big thing is that 50-70 pound sensor that I installed in the bedload itself that was reinforced actually moved all the way downstream to this gauge and got wedged here, right where the salmon hatchery, this facility here controls water stage that goes in to the salmon hatchery at the lower end. And when I was measuring this the other day, I looked down and I kind of see this orange thing. I could see this metal, and I was thinking, when I was here doing cross sections, I was like, there's no way it must be there. This material couldn't move. But all these things are to say that bedload is moving in the channel, and it's moving after peak flow events. And we may have been able to characterize how much water is needed to actually move material downstream. It will take a lot of more inferring and analysis to really decide if this is due to the rinsing, if you will, or washing of this fine material that's reducing the cohesion in the streams, or if the system itself is just is re-equilibrating as we speak and as the channel recovers. This might be, the normal at this point, with the recovery being about 8 years and not 10 years. So a way to kind of fix this missing gap that I'm having now with the water stage is to do flow monitoring through the cross section. So this is right below, a few feet from the gauge that I installed. And doing this, I'm creating a rating curve through this. I'm taking flow measurements at every meter across the cross section and at different flow rates. And eventually doing this numerous times will create a best fit curve. Unfortunately, I've only done it 3 times, so this is just a very simplified version here. But eventually, if I had flood stages around 5 and not recording, this at some point should reach something up here. And it's with more measurements, this curve will become exponential from what should occur in a stream channel and how a rating curve works. This should eventually become this exponential growth where at 5 feet, we're seeing a discharge of, cubic feet or meters per second. Just discharge that's, in the field, we would not be able to have seen this at the time that the flood happened. It would be great, but that's both unsafe, kind of impossible. It would have only been helpful if, for some reason, this gauge system that we installed in summer with the methods that we use would have actually retained this. But, you learn from your mistakes, and not necessarily a mistake, but it's an unexpected consequence of these floodings that we're seeing this year, actually. So to continue the work, as I said, I'm a second-year master's student, and I would like to continue studying this throughout another full water year. However, advisors saying you kind of stop because of these flooding events, but I still think for consistency and because of the sake of understanding how recovery of a fluvial system is after wildfire, I will probably most likely continue to keep performing LiDAR scans, so I can at least perform analysis in cloud compare with the terrestrial LiDAR. I need to continue making this rating curve, more pebble counts. I'm considering reestablishing a gauge so that way, maybe something that's actually on the bank and just accounting for like 2 feet of error that is actually in the channel when it would have been there to maybe record another true flooding event that occurs next year. Because from what we've seen, this is consistent. These floods are consistent. It just may be that the magnitude that they are may have been increasing. This could be to other climatic, climate variability, La Nina, El Nino. I'm not the most versed on that, but 2017 being, or 2019 being maybe one of the opposite years, and we're in a rainy year now. These are all elements that might be driving this movement of material and this recovery of the system. But I plan to continue monitoring this whole river channel and continue doing this work at least through the spring of 2026, depending on if anything else comes up. And then eventually, by the end of it, with the scans, with the LiDARs, and with the changes in surface elevation, I'll be able to calculate that bed load transport rate as it is now, and using modeling software where, if there's an equal input to equal output of what the steady state was before the fire, just to see how far we are from it. Is it a negative? Is it a positive? Or have we reached a different form of recovery? And with that, I just want to thank you all for being here. I want to thank my advisor, classmates, colleagues that have all helped me learn how to use this software, learn how to do this, just kind of be in the field with me while I spend hours doing scans, or and just willing to hear me out and just listen to this project. I really appreciate all of you being here. Appreciate all the help that I've gotten. Appreciate GSOC, honestly. I'm glad that I'm in a university that there's an organization that backs my colleagues and myself and wants us to continue doing the work here in Oregon. And here's some references. But I would love any questions or any feedback you guys have. I'd appreciate any of it.
Thank you very much, Cody. And I was working for the Forest Service at the time with that fire, and I didn't work on the fire, but it was one of those events, and that's why I'm hoping Clark is still on board, because one of the questions, and folks, feel free to pop your questions in here. And actually, Cody, welcome to the reality of doing stream studies.
I like it though. It's fine. I like that.
Because you do get surprises at times. And I think it's fascinating watching that change. And one of the things, and I don't know if part of your study would recognize or factor this in, because I know you're focused on the drainage itself, but your photographs definitely show the reestablishment of the root strength and
Yes.
vegetation. And that's pretty critical. That's
Mhm.
usually at 5 years, if you've got a rain on snow event, at least, and that's with some of the studies, that's where you're at that break point with root strength and
Okay.
things really collapse. And by the time you get out to 10 years, which I think is really fascinating, that's why it'd be nice to see you continue on a few more years, is actually, okay, are we back to how this landscape, coming up with a question for you, Clark, how this landscape is back to normal reaction?
Mhm.
And Clark, my question, because I should be a little more in the know, those drainages are, that Eagle Creek Formation is sedimentary. So what is the potential for the type of cobble gravel component that's greater at the lower reaches as opposed to coming from the basalts up top?
I am going to defer that. I don't know. I don't know.
Yeah, Karen, sorry. I would also say that I might not know.
I don't know because I have not looked at ever at the Eagle Creek Formation. I've driven past it. You point your finger out the window at it. It's pretty cool looking. But after that, I'm on my way to the Dalles or somewhere else, and I haven't looked at it. I just have not worked in the middle of the Cascades, the Western Cascades, all that much.
Well, I have hiked up Eagle Creek, and
Yeah.
that was one of the ahas for me, is just the density, how different that Eagle Creek Formation is low down and high gravel cobble component, and then you
Mhm.
get up around the corner and it's changing into the basalts. So that to me is one of those other pieces. I don't know if you factored that into your gravel studies, but that would be something to think about.
Oh yeah, I will consider doing that because I truthfully I haven't hiked Eagle Creek yet. If I'm being honest, I made it only as far as trail. It's long. It's been a terrible, just different things. I need to do it, but I wanna hear you out here because if I go there and I see that, I'll probably have another aha moment and be like, you're right. Why is it? But maybe it is just downstream sorting, hydraulic sorting. It's just doing its thing, and those things aren't gonna move that way. But the things that erode and the things that break off, they're gonna make you do a new gravel channel down below.
Thank you, Cody. Your presentation was absolutely excellent. We really enjoyed you coming and talking, and we look forward to hearing from you again.
You will. I appreciate all of you. Thank you for having me.